And here we are taking a look at Project 4. Project 4, well, now we're beyond CPU, multi-core parallelism, and OpenMP, and we're going to look at single instruction multiple data. And as you saw in the single instruction multiple data notes, there are several different kinds. There's 2 floats at a time, which was the original. SSE is 4 floats at a time, like 4 pairs of floating point numbers. There's also 8, there's also 16. For SSE, we can count on being pretty much on every single computer that you have access to. So that's what we'll use. But know that depending on what machine you're on, you might be able to do 8-way SIMD or 16-way SIMD. We're going to do 4. Okay, so there are many kinds of problems in science and engineering where you want to multiply arrays of floating point numbers together. Sometimes all you want to do is multiply the arrays together and come up with a third array. And sometimes you want to multiply 2 arrays together and add up all the products and come back with a single sum. We're going to do both. So the first type, I call this, C of I equals A of I times B of I. And the second type, I call this, the sum equals the summation of A of I times B of I. And again, we're going to do both. This project has an extra credit, which does use OpenMP, but for the base project, we're only using OpenMP for timing. So don't do a Pragma OMP parallel 4. We're just using OpenMP for timing. So let's talk about the base project. So I'm going to give you SIMD SSE assembly code. And I'm reluctantly giving you that because it works. Yes, there are other ways of doing SIMD, but you kind of figure that you ought to be getting a speed up of around 4 if you can do 4 things at a time. Well, you do the OpenMP SIMD Pragma, you get like 2.8. Some of the other ways, some clever ways of coding, you get like 2.8 or 2.5. You'll do better this way. So there will come a day when I can retire this assembly language and we use higher level constructs to get big SIMD speedups or SIMD speedups that we expect. Today is not that day. All right. So again, we're not using OpenMP. Use the supplied code to run an array multiplication, and I'll show you where to get the supplied code. And then use the supply code to do the array multiplication reduction. Remember, reduction is when you add everything into a summation. Try a bunch of different array sizes. I'd recommend you start at like 1K, 1024, go up to 8 meg. Make it a multiple of 4. Life is just easier that way. Pick enough values to make a good graph, and you've got enough graphing experience now to do that. Run each test a certain number of tries, and this is just to try and get the peak value. Okay, keep track of the performance and go with the peak. We'll not be graphing performance though, megamoles per second. We're going to be graphing speed up. And speed up in this case is going from non-SIMD to SIMD. Okay, and so speed up, you could do it as performance of the SIMD divided by performance of the non-SIMD, big number over small number. Or if you wanted to do elapsed time, then it's elapsed time of non-SIMD over SIMD. Again, big number over small number. Okay, you're doing this for the A times B, and you're also doing it for the summation of A times B. Now, this would give you 2 graphs with 1 curve each, and that's what you can turn in, and that would be fine because you're going to be graphing speed up. So you've got 2 experiments. If you want to do it as 2 separate graphs, you can. If you want to get them on the same graph, you can do that too. But somehow you must end up graphing 2 terms. Again, this is not a multi-threading assignment, so don't worry about a numt and don't worry about using any pragmas in OpenMP. Your y-axis performance units, again, will not be megamolts per second or anything like that. It'll be speed up, which is dimensionless. There's no units attached to that because, well, when you compute speed up, both the numerator and denominator have the same units. Okay, parallel fraction. No, doesn't apply to SIMD. Remember, there's that n over n minus 1. We have no n's here. The n is the number of cores. All right, what do you put in your commentary? Well, you've got two tables. You've got two curves on either on two graphs or one graph. You're showing what SIMD can do for you. Okay, and what patterns are you seeing? Does it look like it does when you're doing OpenMP parallelism? Okay, starter code. Click here, click, there it is. But yeah, here's kind of the main program, and I filled all that in for you. You get to fill in this. How would you multiply two arrays and put the results in a third array if you had to write it in C, and you do? How do you do the summing? Yes, you have to fill those in. Here's the assembly language. We'll discuss it in the SIMD notes, so I'm not going to discuss it here, but it works. Well, it works on Flip, it works on Rabbit, does not work on Visual Studio. When you do things in assembly language, you're sort of at the mercy of the assembly language format of whatever you're on. And if you're on Flip or you're on Rabbit, you'll be fine. This will work perfectly. So here it is to multiply two arrays. And this is the equivalent of what you're going to do up here is the non-SIMD mul. SIMD mul, non-SIMD mul sum, SIMD mul sum. And again, assembly language, it's different because you're summing. Okay, that's it. Now, if you want to, you can copy and paste that, or you can right click. The way you download things is you right click and you say save link as, and yep, there it is, all4.cpp, and you can put it where you want it. Okay. Yeah, I recommend the script. Yeah, by now you should be getting good at the script. Okay, warning, warning, warning. Do not use any optimization flags. Optimization flags jumble up the use of the registers, which of course will totally goof your assembly code. Do not use minus capo or minus capo 3. Now, there is an extra credit with this. 5 points extra credit. Now, if you want to use OpenMP beyond just timing, you can. Combine SIMD with OpenMP. Okay, and it mentions this in the SIMD vector notes, and this is the graph. So you're going to be producing a graph that looks something like this. It'll probably be different, but this is what I got once upon a time I was doing it. Combining SIMD with multi-core, and it shows you here exactly how to do it. What we're doing is we're using that single program multiple data, SPIMD. See, Pragma OMP parallel. We're not saying parallel 4. And what we're doing is, say we've got 4 threads. What we're doing is we're only processing the first fourth of the A and B arrays. That goes to thread 0. The second fourth goes to thread 1. The third fourth goes to thread 2, and the fourth goes to thread 3. And that's what this is doing here. Okay, this thread, it's finding out the thread number, and then it's figuring out which fraction of the A and B arrays to use. So yes, there we go. Right, and you'll probably get something. Yeah, it probably will not look exactly like that, but it should come close. So here's the rubric. Basically, we're looking at your data, your graphs, your commentary about, well, why do things seem to work this way, and possibly 5 extra points. So, yes, we are now moving on to something different. But I think you'll enjoy this because this multiplying of arrays is a constant theme in a lot of science and engineering uses of computing. And nobody seems to know that this SSE is there. And so people are sort of wasting a factor of 4 because they're not using the tools available. Well, now you are.